Well, I have lots to show you, and so I'll just start right away. This is from 1992, when we did some of the first full-scale casts of concrete and fabric, making columns. And for me, it was a kind of revelation that there was a new world of architectural form, and eventually I found structural form by having a container for the wet concrete that has no particular shape until the concrete arrives. And the idea of a mold and a casting material that would mutually find their own geometry was extremely interesting to me on a number of levels, as a sculptor, but as an architect, also as a builder, and I suppose also a kind of intellectual thrill as well. That's the Center for Architectural Structures and Technology, my laboratory in Winnipeg, Canada. And in here we make mostly models. We use light fabrics and plaster to model industrial fabrics and concrete. So we live in a miniature analog construction world. And our work is a mixture of, I have a background as a builder, so it's a mixture of construction culture, fine arts, methods of wandering and getting lost and finding things, and choosing and changing your mind as you go along, of first principles of natural law and engineering thinking and architectural thinking as well. So it's a kind of a strange mixture of methods, and we do them all at the same time, more or less, but freely flowing between one method and another. And drawing is quite heavy. We draw a lot. We actually don't use computers there, and I was very happy about that for decades. Now I think we're missing them. And so we're ripe now for some of the work that I know is going on here, and Diederik's work is extremely welcome for us, because it fills in gaps that we are just entirely missing from my own work. We painted the walls black so we could draw full size. These are our CAD drawings. We call this chalk-aided design. And with the chalk-aided design, we can, when there's a construction detail, we go to the wall and we draw it full size, at 1-to-1. And I know you can also do that on a computer screen, but there's something quite tangible. It feels almost like you're building it when you have it 1-to-1 in front of you. And you can even check whether a welder will be able to get in and see a weld if you've drawn the thing at 1-to-1 somehow. You can really satisfy that requirement. So we play with material. And I was telling Philippe this, I may have said this 2 or 3 times already to Philippe, but I like to describe our research, the fundamental research, not the applied research, but our fundamental work. It's not like having a bullseye that you try to shoot the center of with a rifle. It's more like shooting a shotgun against the wall and drawing bullseyes around all the holes. So with this method, we never miss. We always find something, and the intellectual problem is to identify what it is you found and to be able to see its use value in some way or not. Maybe the bullseye you draw around it is that this is useless. I can't think of a thing to do with this. So that's the bullseye of that one. So by playing, we can find. And the forms that we generate are those that are given to us by the materials themselves and by the actions and the materials themselves. So we're working backwards from a normal design methodology where first you come up with the form and then you figure out how to build it, for example. So after we take our most interesting ideas from the little models and we scale them up. Generally the models are around 1-to-10, and we can go directly in one jump from 1-to-10 to 1-to-1 and build a full-scale prototype. We can also test them. We have a small, strong floor and a physical testing capability in the laboratory. And our engineering friends are invited to do that. So this was some time ago when we were just figuring out how to cast things full size. We were taking the models and bringing them to full scale. So this is a method of casting precast wall panels using a very inexpensive geotextile. This is a geotextile used in road construction. It costs about $1 a square meter. And here you see our strain gauge and our tensioning device, putting a pre-stress, about a 2% pre-stress in both directions on the fabric. And there's one backbone, a spine of support that you saw running down the middle of it. So you can get a feeling for the tension and resistance. Nothing sticks to this material. It's polyethylene or polypropylene geotextiles, and concrete doesn't stick to them, epoxy doesn't stick to them. They won't tear. If you cut them and put a force on it, they don't tear. They're, in a way, they're the perfect construction material for these kinds of constructions. And here we are placing the concrete, and of course the fabric is now going into its natural tension-resistant form. So that was the first time that we pulled one of these off the mold. We didn't know, maybe we'd lift the whole frame and fabric with it. We had no idea whether it would work or not. We're working here in a precast factory, so we're working with the workers on the floor and with the engineers and the managers of the factory, so we're getting a very good education over the years in how the precast factory works, the culture of the place, the tool kit, the pace of the work, and so forth. We'll just go a little bit more on this. You see now we've subdivided the supports into many smaller supports. Okay, let's leave this. Let's leave this and move on. That might give you some idea of the kind of what a construction is like with this material. It's a true construction material, these fabrics. They're not delicate in any way. The strength of the fabric is never a problem for us. A concentration of stress might be, but that's easily solved by how you hold the fabric, the construction detail. This drawing, this is another CAD drawing. This is how you make a variable section member with a flat rectangle of fabric. 2 tables and a space between, and the rectangle which is pulled apart here, making a shallow deflection, and ruched in to the space between the tables, making a deep section. And with this method, you see this was a rectangle, so you can see already we're casting a bending moment shaped beam. In this case, there's a hem sewn into the fabric, the edge of the fabric, and there's a 15 millimeter steel rebar that's used as a spline to make a completely smooth curve. And this one is 2 pieces of fabric held together with a little keel, and here they're held at points. So 2 different construction methods. The one that's held at points gives you these kinds of undulations in the fabric. So the cheap and dirty construction method gives you a kind of ornamentation. The construction detail is the production of an ornament, you can say, because the mold material is a sensitive network, and anything you do here will have an effect across the network for some distance. This is another way of holding the fabric to make a beam where we don't have a table, but we just use these pipes. And in the space, and then you see these 2 pieces of plywood. So that's a flat sheet of fabric, and that's a flat sheet of fabric. And they're held together with a curve along the bottom, and that produces a perfectly smooth surface. And the game here, of course, is to reduce the amount of material that we use in a beam. So if we can follow the natural force path through the beam, the bending moment curve, we think that we can save perhaps 30% of the concrete. And I won't go into this here, but these beams have only 1 piece of steel in them. There are no stirrups. There's no cage built into these beams. The tension force will tend to stay along this line of the bending moment curve and not move up into the web portion of the beam as in a rectangular beam. Now, the devil is in the details, and there is some issues at the supports That's the subject of PhD research at my university in engineering, PhD research, my engineering in Bath University. There are 2 PhD students working on that currently, and a guy who's just finished up in Edinburgh. So we have the construction method, and then the question is put before the structural engineers, how do these things actually behave? And the fundamental principles are sound, but of course the matter has the last word. The game is, if we can get these things to work, we think we can save 30% of the concrete and maybe 40% of the steel. Still have a ductile failure and so forth. So that's that research. Here's a more ambitious beam. This was actually the first beam that we did. This is a 12-meter beam that's cast in a single flat sheet of fabric. Everything I'm showing you is cast in flat sheets. We don't tailor the fabric, and that's a decision a constraint that I've made because I'm a builder, basically. So I'm very interested in dead simple methods that anyone could use anywhere in the world. That's a kind of primitive constraint that's been very fruitful for us. And we think this may be the volume of concrete that we can save if we can figure out the reinforcing details. Oops, that's missing. That was the piece of fabric that was for this beam. I don't know if you can see. That's my very small daughter, actually. Now, if you make cutouts in the 2 tables and you stretch the fabric, you can make a ribbed T-beam. Again, just 2 flat sheets of fabric. And there's a Photoshop ceiling of roof structure or floor structure using this method. This is from the plaster models, using the plaster models. So here's an example of, this beam has only one piece of steel. So there's an anchorage here, and the steel runs along like that, and another anchorage there. And here we are, it's a 4-point load, so it's approximating the uniform load, and you notice that all the cracks are 90 degrees to that one piece of steel, and there's no shear cracks, so-called shear cracks, running diagonally through the beam. As the beam gets stiffer, you will develop a kind of, I don't really know if I call it a shear failure, there's a kind of rotation or moment. It's so difficult to name these things properly because the beam has no names for them. It's our concepts. It's how we might conceptualize them. But this is that's an example of the behavior of these more efficiently shaped beams. If we think about these cracks, you say, well, now, as soon as it's cracked there, the concrete's doing nothing. So if we want to reduce the concrete further, we could just take away the concrete everywhere the beam's going to crack. We say it will crack, so let's just take away the concrete where the cracks are. The beam will be no less strong for that, and we'll save some more concrete. So here we're just pinching the two flat sheets of fabric are being pinched together at approximately the crack spacing for one of these beams. And of course, what we're doing is inventing the truss, our invention, that we came at by some strange back door of cracked beams. It was a kind of embarrassing moment to invent the truss, but very interesting because I had never conceived of a truss this way. It was a new idea of what a truss was. And here we have these, instead of pinching the 2 sides, now we're going to just build each side of the mold stretched around what we call impactos. This is an impacto in our language. And here we are stretching, very similar to the ribbed T-beam. If you pull like this along the opening, the fabric will go down. And there's a 4-meter prototype. And that's the 4-meter beam, 4-meter truss. Now, it's quite surprising that the flat sheet of geotextile would make these curves, but it does. We're always surprised by the fabric. And I've been using flat sheets of fabric for 25 years now, and it still is giving us new forms, sculptural, structural forms. It's not done yet. And I don't know where the end is. I keep thinking this year, surely we must have the last possible form, but it's not true. We're taking now the same frame that you saw in the movie, and instead of stretching the fabric, we'll hang it loose. This is 2004, so that's quite a few years ago now. And we're spraying a GFRC, a glass fiber reinforced concrete, so random fibers chopped into a special mix design. And that has to be compacted. That then made this mold from which then we can precast a series of funicular compression shells. These are very primitive compression shells, just a barrel vault, and it's quite small. This is only 2.5 meters, something like that. So it's a large model, we could say, of a possibility. But it worked, and we stopped until sometime later. 2 years ago, we picked it up again, this idea of the fabric-formed vaults. Here are the pipe stands that you saw from the beam with the yellow fabric. Remember that one? So we pulled out the pipe stands again, and these are pipe stands we've made where we can raise and lower them. And we have a hollow steel section, a piece of plywood. So now we have a curvature this way along the span of the member, and we have, let me go back, and we'll hang a piece of fabric here between these supports all the way down. That will give us a double curvature to this flat sheet. And then we had mortar mix and carbon fiber mesh. So that's about 3 centimeters thick. There it is. So again, these are very small, but big enough for us to work through and think through of full-scale connections and full-scale construction techniques. Here's another version of this where these are the same curved edges from the pipe stands, but now this is 2 sheets of fabric, again sandwiched in the middle, with a kind of with a form-active curvature for the center of the beam or the shell or whatever this is. It's a kind of flayed beam, like if you skinned a beam, you would have this kind of shape, perhaps. This is a numerically generated model of a piece of fabric hung from 4 corners. And you'll recognize these buckles. We all know this. When you pick up the sheet from your bed, from the corner, it makes these buckles. And these were generated from some models, physical models, of course, that we've done, where this is now the mold. So you have to imagine now the preceding steps. This is a yellow plastic-coated fabric that was upside down, held at the 4 corners, and sprayed with plaster, so it hung under some imposed uniform weight, and it formed these buckles here. We backed it up with more plaster, turned it around, and made a mold like this, and then cast this shell off of it. The fabric, which buckles along the principal line of tension stress, provides deep corrugations in the mold for a funicular compression shell. It gives you a buckling resistance section along the principal lines of compression stress. And this is all self-forming. The materials know to do this. Now, when I pass this idea by my engineering friends and I say, is this some corollary to the reversal or inversion of the chain that hangs and the arch that stands, of tension and compression, geometrically reversed? Maybe the buckling of the tension membrane gives you some kind of optimum buckling resistance in the shell, in the reflection in the shell. And I've never met any engineer who would actually answer this question. They just stay quiet. They don't want to say anything. And finally, I was in Bath with my colleagues in Bath, and I finally wrestled Tim Eibel to the ground, and I put my hands on his throat, and I said, "Talk to me like this. Tell me, say something." And he said, "Okay, the reason I don't want to say anything is that buckling is very complex, and I don't really want to say anything about optimum anything." He says, "I agree with you. When I look at these things, they seem to be forming themselves in the right places. The right thing is happening. But it's terribly complex to say." So my proposal that this is some sort of a natural symmetry is up in the air. And I don't know if it interests any of you, but if it interests you, I'd be very interested to see whether this couldn't be established or thought about in some way. I only see it and understand it as such. I can feel it to be true. But that's a kind of, that's a possibility. Here you see another kind of vault where this is, it's a square, so there's almost no load here. It's sort of, the load is balanced between these 2 points. And look, it's made a kind of compression arch. It's a discontinuous arch, but the fabric buckled in its own way, offering a deep structure along the principal compression arch of the vault. You can induce a buckle as a pre-stressed buckle in a piece of fabric before you even load it with concrete, simply by pulling on it. So if you pull this way, you'll create what we call a pull buckle. That's a push buckle, and that's a pull buckle. Push buckles can go anywhere. They make up their mind. There's an infinite number of solutions for them. And the pull buckle, there's sort of one solution. You go from here to here. You can form it slightly differently, but that's here's two pieces of fabric that have been pull buckled and then loaded with a spray plaster. And you see they now present us with a kind of barrel arch, or barrel vault, I should say, barrel vault, but one that provides buckling resistant double curvature. It's just a flat sheet of fabric. Here's a drawing of it's a conception for a shell structure or a kind of beam, another of these skinned beams, where on both sides you'll have a funicular compression vault, a thin shell compression vault. But their thrust is collected by 2 end beams that are tied together with a straight line of tension between the 2, like we say, thrust beams, we'll call them. And this can be formed by having a pull buckle that runs down the center of a piece of fabric. That helps the fabric do a flat piece of fabric take this shape without getting a bunch of wrinkles and buckles that would be, let's say, non-structural shapes. This is a piece of fabric that has a fuzzy backing on it. I had this manufactured for us by a textile manufacturer. The bottom side is plastic coated, and the top side here is fuzzy. So it will, the concrete, when we put the concrete on it, it will capture the fabric. So there's our little model where we worked up the methods, and here's the full scale, 10 times larger, 10 times longer. And here we are now putting glass fiber reinforced concrete on the fuzzy fabric, fuzzy back of the fabric. And this would be a spray application in an industrial setting. But I'll have a kind of test in my own mind, a kind of question, would this method be possible in rural India? Let's say, I don't know, I've never been to rural India. But it's a kind of idea in my mind of how, can we bring our methods to the most primitive, simple production level in terms of equipment, tools, and so forth. There's the mold, which we turn over, and there you see the plastic coated reverse side, now the front side of the fabric. And you'll notice that the fabric now has also formed these large pull buckles running along the principal lines of compression stress. This is the tension zone running back along there, and here's this funicular compression shell mold with its buckling resistant line of force. Here it is ready to be cast. We scan it to get a three-dimensional scan so it can be analyzed for reinforcing patterns. And because the mold was made from a flat sheet, we can also use a flat sheet of reinforcing mesh. And the reinforcing mesh will take exactly the same shape because these are all flat sheet shapes. So here, this is an AR glass mesh, alkaline resistant glass mesh. And here's our, now we're just using a regular mortar mix. and there's the shell. Now, when we pulled this out, there were very large, for us, very large demolding forces. And we did everything right. I'd worked long enough in the precast factory, so I knew the regime. We had compressed air, release agents, everything. And we got it off. But when we brought this outside, the first time it rained, at the hoist points, we saw it's just cracks. We cracked the hell out of the vault getting it out, because it's so thin. So it's a very thin thing. So we had to do something about that. And Rani Araya, my research associate, said, well, let's use the same fuzzy fabric again. We'll put it down as a prophylactic. And so you can take this thing, put it down, pull it. It takes the same shape again. And this vault now has a fabric. It's captured the fabric. That fabric layer is now captured onto the surface of the mold. That has some problems maybe, but it gives you a spectacular finish. Like it de-skills the finishing of the surface of the mold. This is about 6.5 meter span. And this is a science fiction shot. That's Photoshop. So we didn't have to cast 3 of them. We could just fake it. Now, this is a drawing sent to me by Byung-Soo Cho Architects in Seoul, Korea. And this is a corporate guest house and visitor center for a large Asian construction company, the Hanil company. And this is their design. They said, okay, we want to do these as tilt-up walls, so cast on the ground and then lift up into place. And we don't know how to do it. Do you think it could be done in fabric? And I thought it was an interesting problem because we'd always done either a convex cast or the shell concave cast, one way or the other. I'd never done a cast which was both convex and concave, so that's interesting. So I did some sketches, photographed or scanned the sketches, sent them as JPEGs. We built some models, put some arrows and instructions, sent those as JPEGs, and models of the plaster, photographs of the plaster models that we made, and then they built it. We didn't train their builders. I never went there. They worked off our JPEGs and our arrows and instructions and made. First, they built 5 full-scale mock-ups using 5 different formwork methods. They chose the fabric one, and some applications can be tricky, and you would want to practice and learn the ways of the material, and others are just dead simple. Lots of them are quite simple. Well, this building is not to my taste, but I'm very happy that they built it, and it serves as an example of how simple the technology is and how simple it is to transfer the technology. This is Rani Araya, my research assistant, going crazy with push buckles. He got very interested in the buckling, so he just buckle everything. And here's some full-scale panels. You would think that if you buckled a piece of fabric and then put 10 or 15 centimeters of concrete on top of it, that it would flatten the buckles, but it doesn't. That's very interesting that it doesn't. There's enough fluid pressure in the matrix that it actually is just making a kind of arch. It retains this very thin arch. That's the concrete. You can see the location of some staples that were holding the buckles in place. And here's some more of Rani's buckled panels. These are now in plaster models. But everything we can do in a plaster model can be done at full size. They have never failed us. So we know that if we build it whatever we get, we can do something like that. The proportions will be different, but the events will be precisely the same. Here's Rani buckling a flat sheet in another way. And this we know this sort of chevron shape. This is a vocabulary of the fabric sheet. which we know. It's just absolutely ordinary, but here they are rediscovered as a kind of architectural language. I'll show you another project for construction. This is the current project. We're working on this right now. And this is a new hospital building in Winnipeg. So it's public money for a new women's hospital. And it's done by a large corporate architecture firm in Winnipeg. And this is a fritted glass facade with images of trees. And there's these big diagonal columns. This is the entrance court. We're doing, I won't show you this, but we're doing some fabric cast, I call them worm benches. They're kind of funny fabric cast bench planter things. But we're doing that, and we're doing an entrance canopy cast in fabric. For the canopy portion above, we thought it would be very nice to do a shell. Maybe take some of our shell technology like the one that I just showed you and see if we couldn't do something sculptural with that. These are not strictly structural shapes. It's more of a sculptural project. The width of each of the slabs, there's 6 slabs, if we can afford 6. There's 6 slabs that go down here. They're all the same slab. And the columns are all identical as well. And each slab is 9 meters by 3.5 meters. So the spans are quite small, so we reckon that we had some freedom, geometric freedom and sculptural freedom with relatively small spans. So here's this, this is a fuzzy-backed fabric stretched over some impactos and pulled down or pushed down with these tension things. It's just pushing down the fabric so that it makes a topography. We spray plaster on the back of that, flip it over, and this is our mold now. That's the topography that's formed. And this edge is made just by shining a laser, like a surveyor's laser, onto the mold, and it makes a kind of water line, a section cut. So we just follow the section cut and then cast off the mold. We thought these could make really interesting and beautiful canopy ceiling as a shell. Here's another idea. We did many of these, many shells, thinking through the geometric, sculptural, structural possibilities that the flat sheet could give us. That's a cast, a kind of close-up of the detailed ornamentation that the flat sheet gives us. We brought in the guy from the precast factory who will produce these things, who does their pricing, and we said, okay, how much for the shells? What will it cost to produce the shells? And he said, I can't tell you. We don't do shells. I can't give you a price. And I said, well, what can you give me a price on? And he said, I can give you a price on a flat slab. We don't want to do a flat slab, but we have to do a flat slab. We're in Winnipeg. You know, these guys kept telling us, this is not Barcelona. That's what they kept saying. Okay. So, flat slab. I remembered a project we had done very briefly for Herzog and de Meuron. It was not really a project. It never happened. This is a very high-priced residential tower in Manhattan that they were designing. They opened an office in Manhattan to do this building, but it was financed by Lehman Brothers, and so it's all vaporware. The whole thing is vapor. But they had a problem on this building because in New York City, I don't know if you know this, but in New York City you cannot get good concrete. You cannot get architectural concrete in New York City. The concrete industry is a kind of mafia, or maybe it is a mafia. And they give you what they make, and that's that. So Herzog and de Meuron are desperate. They have a fifth facade, which is the underside of all. If you pay $1 million for your condo, you look up and you see crap. That's a problem. So they came to us and they said, well, could you help us? So maybe we can do something for the underside of these things. I think we can do something. So we had the idea, this is a notional model. This is not the actual model. It's just to think through the idea and give them the idea. We have a normal plywood deck for the formwork, and we make cutouts in it and put a membrane across that and cast into that, and that's the underside of the slab. So that's an idea. But then Lehman Brothers went the way they went, and the project disappeared. But the idea was still there. So I said, okay, a flat slab. We have to make a flat slab. What if we take the formwork and we cut out holes where the capitals will be at the column locations, and we push the fabric in, and here comes Ronnie's buckles. Well, we got buckled fabric. If we cast on top of this, these buckles would cut into the structural section of the flat slab very bad. So we want these buckles to disappear. So we mapped out their location just by pushing a pin through. We drew where the buckles were and then cut out where the buckles are. And now the buckles will go downwards instead of upwards. We give them a place for them to go down instead of up. So this is a kind of design. It's a kind of design. I mean, some of these things we drew, like we drew this one, for example. That's our design. But these are given to us by the fabric. So we're taking dictation from the buckles. This is another approach where we say, no, we'll decide. We'll make a geometry and cut lots of gutters, just lots of places for the buckles to go. Whoever wants to buckle can buckle, and we'll just push you into the hole, like that. And here's our model, and you see these pins are modeling a staple gun at full size. Later on, we learned to use a vacuum, so we didn't have to do these pins. That's crazy. That's just too difficult to do. But the vacuum was very simple, and we could push the buckles into the holes. There's Ronnie getting ready to pour. And there's the cast. So two different approaches. One where the pattern of the ribs or the buckles is we take dictation from the fabric, and the other one we can decide something. That's a Photoshop of this kind of canopy roof, canopy ceiling. The one that I hope we've settled on now goes back to the shell method. So here are the 5 column capital locations, and we put bumps, impactos. In this case, they're hemispherical impactos. Put the fabric across it, stretch it into place, then spray a stiffening plaster to capture the shape. At full scale, the full 9 meter by 3.5 meter mold, we hope to do in fiberglass with a fiberglass manufacturer who makes buses, bus parts, bus bodies. So there's the mold. And there's the cast from the mold. Here's some details of it. It's a very beautiful thing, and it's like water flowing over rocks. It's just a spectacularly beautiful thing. And these beautiful little stress lines here, these little micro pull buckles. That's one of the hemispheres there. So that's the capital. And in previous designs, we'd had circles as capitals as circles, or capitals as a cup, where the column is pushing up, squashing the fabric. But in those cases, the location of the column top and the capital and the slab have to be very precise. Like the construction tolerance is extremely small. And I didn't think that the precasters would be able to do that in this case. The columns, as you'll see, are angled, 2 different angles, and it's Winnipeg, so I said the workers will need a much bigger construction tolerance. So we decided that this water flowing over the rocks could just continue. It would be uninterrupted, and we'll just provide a kind of bump in the capital. And then we have a weld plate on the top of the column. So the top of the column is actually circular, not in this case, but they are now circular. And as long as the center of the hemisphere and the center of the column are near each other, within some centimeters, then we have a sufficient alignment. And we designed a very simple hollow steel section, welded connection for the top. So we're at the same time inventing new, let's say, connection details for the precast industry as a way of solving the architectural problems or opportunities. The architects who asked us to do this canopy for the building had seen this photograph and had seen these models from previous work. And so here's some of our shells and these branching columns that I'll show you a little bit about. And so they thought that maybe that might be an interesting, for the women's hospital, it might be an interesting thing, sort of, I don't know if they're women or trees, like the facade, something like that. But there was on the client committee, there's a nurse on the client committee who thought that it looked like vaginas. And in this case, I totally disagreed. In this case, maybe it's like, she might have a point. Women's hospital, public money, client committee, so we have a problem. And everything that we do when we're pouring a plastic wet material like concrete into a tension membrane is going to look like a body or a vegetable, mostly a body. I have a little bit of high blood pressure, I don't know about you, so I'm only slightly more inflated than you are. But each one of us is an inflated being, and each cell, the cell walls, are in a kind of tension from an inflation. So the similarity between bodies and this way of constructing concrete is not a coincidence, it's a co-incidence. It's an incidence of pressurized membrane vessels in both cases, or in all of these cases. So we have a problem. We tried clothing the columns, but then it just looked like a negligee. And what we found was the more we tried to repress the eroticism of the architecture, the more erotic it became. And we would have these really unhappy client meetings where we thought we'd solve the problem, but they came in and said, no, this is worse. It's getting worse. So then we thought, okay, we'll make it like really tree-like, and we'll take this crotch and we'll run it down so it's like two tree trunks coming out of the ground. And so we came up with these. Then, people started talking about J-Lo's pants, and I don't know, like what will we do? What will we do? The solution, this very good solution, is we will. Oh, I didn't put that slide in. We'll bury them. And I like this solution very, very much, because we'll have a video. We'll put it on YouTube. The burying of the crotches. It's like a conceptual art piece. Perfect. It's perfect. It's just perfect. We're really happy about that, how that all worked out. But anyone who wants, a fully erotic architecture will also have the video and the photographs and everything. We know how to do it. That's the easy to do, actually, with this method. Here's the model for the columns. So again, a table with a void, and a flat piece of fabric will go in here. And this is the troweled flat surface of the columns, and then the round surface is the other side, curved surface. That's the Shroud of Turin pulled off of this complex three-dimensional curved thing back to its flat sheet. There's the fabric in the mold, filled with plaster. That's the underside of the mold. And here's a model of these things. So that slab is the same as that slab, and all the columns are the same. There's only two molds. And that's a kind of unit. That's a geometric unit that repeats again, and then repeats again. So it appears to be random, but it's exactly the same cast each time, the same slab. The engineer designs one slab and designs one column. And because of the sort of little half step we do in the rotations, we're able to make a kind of forest, randomized forest, it would appear. That's one of these columns cut. That's a beautiful thing. Oh, it really looks like a bone, so we can't use this. in the hospital. Can't use it in the hospital. Here's another CAD drawing. You see the door handle on it? That's an important detail, so you have a sense of... Then we can get our hands in there to see whether we have sufficient cover, can you tie the steel, and so forth. And here's the sections, different sections through the column. And these are all based on physical cuts that we made through our 1 to 10 plaster models. We don't have the software to tell us what the sections will be. Maybe when Diederik is done, we will. So there's a labor-intensive research that has to be done to do the little construction, cut the sections, and get our first approximation of the sections. And this is a drawing of how we have to cut out the table supports and so forth. The next step for us is to do a full-scale mold. We're building the full-scale mold right now, and then putting fabric in it. And then what we'll do is we'll line that with plastic and fill it with water. And we'll do a full-scale water test, and then we'll know what the real sections are. Oh, pretty close. The concrete, of course, is heavier, but it gives us almost exact readings on the true sections at various points. So we can go back and refine the CAD drawings, make sure we don't go over the property line and so forth. Now, here's a piece of fabric that's been buckled. So these are two examples of the same thing happening. This fabric has been pushed together vertically, and then it forms these horizontal buckles. Okay. In this case, and in this case, in this case, in this case, the fabric has been pushed in two directions, and the fabric will spontaneously buckle into Y-shaped branching figures. It does that. It likes to do that. So here we are with a flat sheet being buckled into a branching shape. This is these Y-shaped columns that I was showing you before. So there's two of these, and the plywood here is just the two sheets of plywood, a two-part mold, are being pushed together like this. And you'll notice that the detail here is we're using a twisted rope. There's no steel in this. We just use a twisted rope to tie it together. And again, this is our search for how reduced and primitive could our methods be and still produce these things. The other thing you'll notice is that this mold is bleeding water. This is a geotextile, and those are engineered to have a certain permeability. You can buy the product you want that has the permeability you desire. So the first thing that happens when you place concrete in a mold made out of a permeable fabric is the air bubbles pass right through. So anyone can get Swiss concrete now. It's like, I don't know how to do it unless we do this. Right? It's a secret, some kind of state secret. The Japanese have their own state secret. But now we have an automatic way to do it because the air bubbles are not retained against the mold. And after the air bubbles pass through, or while they're passing through, we also lose excess mixed water. And that's what's happening here. So it's a filter. The mold is now a filter that's collecting a cement-rich mixture at the surface of the cast. And I had a master's student in engineering working with me and her engineering advisor, with his engineering advisor, doing a series of tests on fabric-formed concrete and concrete cast in a waterproof mold, normal mold. Here's the age, strength. The black is in a waterproof mold, a standard rigid mold, and these are two different geotextiles. So 10 to 15% increase in strength in a, what would that be, 100 millimeter cylinder. That's the detail at the base of the Y-shaped column that I just showed you. So there's no connection. It seems impossible, but it works. You have to have someone at the base of the column making sure that the fabric doesn't ride up when you first place the concrete. But you get about that much concrete in it, and the fluid pressure against the membrane makes the membrane stiff. It takes its tension and it becomes stiff, and then you just go from there. So you have to be a little bit attentive just at the first, but then you can walk away. And that was, by the way, that's a self-compacting concrete that we put in there. A flowable concrete. Zero, not zero slump, like maximum, whatever. Like they measure it by spread, right? You know, self-compacting mixes, if you've ever used them. Quite liquefied. That's the detail. We take a little tuck, the crossing. That's the concrete. And there's our branching column. The idea of the branching column is that it can go up and either reduce the span of the beam that it holds, or it can channel the thrust line of a vault or a compression arch. And these are some photographs from some years ago where my students were making shells and branching columns to just play with the architectural and spatial possibilities, sculptural possibilities that these construction methods offered. Here's the branching fabric in a slab mold. It could be cast in place or it could be precast. And this is Photoshop, like sketch idea of what you might be able to do. And that's a branching column. So there's the center, the trunk of the column, and here's the branches going out to their support points. That's what these guys are. Kind of ceiling plan. And here's one of these branching columns cast with the wall. So all you have to do then is don't push the two sides of the mold against each other. Just leave them, give them a little room for the thickness of a wall, and you can cast a pilaster. And that unit is now imagined as a precast unit, now used not as a wall, but as a branching beam structure. That's the method, a little drawing of the method. Standard wall form, fabric liner that's allowed to deflect out to a greater or lesser amount. And on the inside of the wall, you can then block out the wall mold. So you can only pour, maybe if you want to only pour a section of the wall, just these little bits of a wall to make a buttressed column. And I'm very interested in the buttresses because of the vaults that we can make. We can make these self-forming funicular vaults. If it's a true vault, it's going to have a thrust. So we would like to be able to make a structure to receive the thrust. So that's a standard wall form. There's nothing fancy about this wall form. It's just a slightly differentiated wall form in plywood. That's a 3-meter prototype of that method. And here's some more buttress columns leaning in and sort of preparing themselves to receive a thrust. Here's a hanging sheet of fabric. And we had taken some of these hanging sheets and sprayed them with the plaster gun, and they made the most beautiful plaster thin shells. And so there was a temptation to do it full size. I honestly didn't think it would work, but it was so beautiful that we tried. I paid for much of the time I can get this stuff donated, but I had to pay the guy with the shotcrete to come in and do this. So that's a random fiber reinforced shotcrete. And it worked, more or less. I mean, you can see we have some problems with the finish here, but that's first time. I think it's the wrong fabric. For sure it's the wrong shotcrete mix. Here's another one. That's 3 centimeters thick, these things. They're very, very thin. That's the plaster model. Some more plaster models. So some of these are held vertically, some are held horizontally. You could hold it any way you want, and you'd have a different kind of gravity in the form. And the spatial possibilities are extraordinary, I think. As they're all plaster models, but these are buildable. And I'll just end with some drawings, just to show you. I don't know why, but I'll show you these. These are sketches for a building. I'm just dreaming. But these drawings, which, if I showed them in the beginning of the lecture, might look like fiction, all have construction methods, and there's construction details and wall sections worked out. I mean, these are completely doable things. And these could be actual fabric, or that could be concrete. We could have some that move and some that don't move. And there's a series of drawings. I did this series of drawings some years ago, where I started from, Edward Hopper's painting, the American painter Edward Hopper. Edward Hopper's figures, the people in his paintings, are strangely like puppets. They're unnerving puppet figures. And I was absolutely fascinated with those figures, and I thought that it would be interesting to build an architecture around them. So these drawings were just project the painting, copy the figures, and then project an architecture around them. And it sort of turned into a hotel, I think. Then it looked like maybe a hotel lobby. But everything there has been built either in models or full scale. This one, for example, is a facade where this is the branching column that you saw, but with the mold still on it. So with the plywood mold and everything, we haven't stripped the mold. It's very beautiful in its own right. So the idea was that you simply cast in the mold, and the mold provides the wall, and the concrete infill provides the structure. That's the end of my lecture. How do I do? What time is it? It's perfect. 3:03, exactly 1 hour. So I'm very happy to answer questions if you have them. You'll do this.